Good morning. Today we are going to start solving some exercises related to chapter 4, vibration, rotation, spectra of diatomic molecules. Here I gave you some constants. You may use them whenever you need. The first exercise says, the rotation vibration spectrum of carbon monoxide C12O16 has an intense band in the near infrared in the region of 2100 2200 cm minus 1. With a low resolution device, the following series of lines is obtained. So you can see the different lines obtained. A. Determine the moment of inertia, the internuclear distance, and the vibrational angular frequency of the molecule. Before finding the moment of inertia, it's clear that the spectral lines are equally spaced. If we take a look, you can see that here we have 24, 28, 32, 36, 40, so they are separated by 4 cm minus 1. Here we have something missing, which is 2144. Then we complete there 48, 52, 56, 60. The spectral lines are equally spaced by 4 cm and there is a line absent at 2144. Because they are equally spaced, we assume that this measurement was done neglecting D, neglecting the distortion constant, and also neglecting the difference in rotational constants between the two vibrational levels 1 and 2. Yani B prime and B double prime are the same. Because we have said that if they are not the same, we can see that the distance between consecutive lines starts to decrease as we go with higher frequency. يعني المسافة بين هيدول المفترض تصير أصغر إذا أنا عليت عندي الفريكونسي. This part here corresponds to the R band, which are the rich lines with high energy or high frequency corresponding to delta J equals +1. And this part here corresponds to the poor lines or P branch with low energy or delta J equals -1. Because the distortion constant of this molecule is assumed negligible, in this case the distance between two consecutive lines is equal to 2b. Hence 2b is equal to 4 cm minus 1. رح ارجع عيد كيف عرفنا انه الدي negligible؟ لو الدي منا negligible كنا نحن صرنا نشوف انه كل ما بعدنا عن الجاب المسافة ما بين اللاينز بتصير تتغير. اوكي it depends on D. ما بتضلها كلها نفس الشيء. واكيد هيدا الشيء من الجهتين بالبي برانش وبالار برانش. So A, we note that the spectral lines are equally spaced by 4 cm minus 1. Hence 2b is equal to 4 cm minus 1 and b is equal to 2 cm minus 1. Let me write that we have a line absent. We note the absence of a line at 2144 cm minus 1, which represents the transition of pure vibration لأنه هو عبارة عن انتقال من J0 to J0 فما في عندي rotation, it's pure vibration. Anyway, it's forbidden because the selection rule says delta J must be plus or minus 1 of pure vibration. Okay, we said that we have to find the moment of inertia I. So let's find I. We know that B is equal to h over 8 pi squared c I, implies I is equal to h over 8 pi squared c b. So this is b bar as usual. You may keep it b, it's okay. It's equal to 6.626 times 10 power minus 34 over 8 pi squared. C is 3 times 10 to the power 8. The B is in centimeter minus 1. We have to write it in meter minus 1. We multiply by 10 to the power 2. So we get our answer. It is 1.398 times 10 to the power minus 46 kilogram meter square. I will write it approximately 1.4 times 10 to the power minus 46 kilogram meter square. And we have found I. Now let's find the internuclear distance R. So we have I. Let's find mu to find R. So we have to find R. To find R, first let's calculate mu. Mu is equal to m1, m2 over m1 plus m2, where 1 and 2 are the two atoms, carbon and oxygen. So for carbon, the mass or the molar mass is 12 gram. For oxygen, it is 16, so times 16 over 12 plus 16. So if I'm assuming this is in gram per mole, so I have to multiply by 10 to the power minus 3 to change it to kilogram. And I have to divide by Avogadro's number to get the reduced mass of a single molecule. So divide by Na, which is 6.022 times 10 to the power 23 per mole. So we get 1.13868 times 10 to the power minus 26 kilogram. So this is the mass or the reduced mass of a single molecule. Now we have mu, we can calculate R. You all know that I equals mu R squared, implies R equals radical I over mu. It is radical. So 1.4 times 10 power minus 46 over 1.13868 times 10 power minus 26. You end up with 1.108 times 10 to the power minus 10 meter. And this is the internuclear distance. Now we have to calculate at last the rotational angular frequency of the molecule. It was miswritten as vibrational, but I've changed it to rotational angular frequency of the molecule. The frequency of rotation, omega. So let's find the frequency of rotation. We all know that the frequency of rotation depends on the level of rotation, so it must depend on the quantum number J. So you all know that according to quantum mechanics, the angular momentum is equal to h over 2 pi radical j plus 1, where this j is the quantum number and this j here is the magnitude of the total angular momentum. Classically, this angular momentum is equal to I omega. So it's equal to h over 2 pi radical j plus 1 implies omega, which is the angular frequency of rotation, is equal to h over 2 pi I radical j plus 1. So the rotation depends on the level j, 1, 0, 1, 2, 3, etc. It depends on it. So I'm just substituting for h and I. equal to 7.5 times 10 to the power 11 radical. I'll keep this G plus 1. The unit is radians per second. And this is the angular frequency of rotation. Now the last part says, part B, determine the value of the distortion constant of the same molecule. So we have said, I have explained that the distortion constant of this molecule according to these measurements is neglected. لو ما كان neglected كنا شفنا انه كل ما بعدنا عن الجاب كل ما البيكس عم يقربوا على بعض. اوكي بصيروا أقرب شوي. So this can be done if we choose another instrument, more precise instrument to measure our wave numbers with. So let me write here. So B, the numerical data suggests that the centrifugal distortion is 0. To obtain this data, or to obtain D, it would have been necessary to use a higher resolution device. Okay. The second problem says, the infrared spectrum of DCL under high resolution shows absorption lines whose frequencies are indicated below. So these are the energies or the wave numbers in the unit of centimeter minus 1. Distinguish between lines belonging to DCL35 and those belonging to DCL37. If we look at these energies and their absorbances, we can see that they can be divided to two groups, one having a higher absorbance or a higher intensity than the others. So either we can take a look on the table or we can do a plot. The plot helps us in understand the numbers in an easier way, but anyway it's not necessary. So if we are going to draw these numbers, let me just draw them. I will put the energy here in centimeter minus 1. I will place here the intensity or the absorbance. And we will get something like this. We have several lines which start to increase and then decrease. And again, they increase and decrease. Another group with a lower intensity does the same. It increases and decreases and then increases and decreases. So these dots are these values. So all I have done is that I plotted for each energy the absorbance, and I've got these points. So we can see that we have two groups of lines, one with high intensity and one with low intensity. The ones with low intensity correspond to DCL37 and the ones with high intensity correspond to DCL35 because CL35 is more abundant in nature. If we take a look on the numbers here, so you can see that, let me go just down because they are more obvious. So you can see that each two lines are very close to each other, one with high intensity and the other with low intensity. So let's take for example here, this one has a high intensity and the one just beside it has a lower intensity. This one has a lower intensity. Let me choose another color. If this one corresponds to DCl35, this one also corresponds to DCl35, this one, this one, this one. No, they have a higher intensity. And this one, this one. This one corresponds to DCl37. You can see they correspond to DCl37. واحد هيك واحد هيك. And similarly from the other side. Okay, so it appears clearly that there's a group related to DCl37 and a group related to DCl35. And each group of these is made up of two branches, a P branch and the R branch. And we can see that there's a missing line in the middle. Approximately, we can say that the energy of the missing line is equal to the energy of the first line in the R branch plus the energy of the first line in the P branch over 2. لأنه هن symmetrical بالنسبة للميسنج لاين، so جمعهم على 2 رح يعطيني الميسنج لاين. So here if we take a look on the lines corresponding to DCl35, which are the blue ones, look at the intensity. So the intensity is, let me use the blue color, the intensity is 1.709, then 2 is increasing more, reaching a maximum, increasing more, here they reach a maximum, so the maximum is here, and then starts decreasing again, 1.096, then 1.761, here we started increasing, so it's 2.1. So we take the two lines that are symmetrical around the missing line. So where is the missing line? According to the intensities, the missing line of DCl35 must be somewhere between this and this. How did I know? I took a look on the absorbance or on the intensity, and these two intensities are the minimum. So you can see here it's 1.8, it's higher than 1.1, and the one following the one that I have chosen up is also higher, so 1.7 is higher than 1.096. So obviously these two lines are symmetrical around the missing line. So this one with the lower energy, this one has a lower energy, the previous one had a higher energy. The one with higher energy is R0 and the one with lower energy is P1. ما تنسوا البور عندهم lower energy والريتش عندهم higher energy or higher frequency. So كل lines اللي هون they are from the R branch, and the lines that are here are related to the P branch. So this is the P branch. So let's write the answer of part A. The first group consisting of more intense lines corresponds to DCl35. So this group has a missing line. Let's find this missing line as an approximation. It's not required, but I'm just finding it. So the energy of the missing line, which corresponds to a pure vibrational transition, missing grade, it's equal to, we said it's the energy of R0 plus the energy of P1 divided by 2. So according to our table, it must be 2101.6186 plus, going up to the table, it is 2080.275. All of it divided by 2. must be equal to 2090.94 centimeter minus 1. So same for DCl37. So for DCl37, the energy of the missing ray is equal to the energy of R0 plus the energy of P1 divided by 2. So if we look at the table again, let's look at the table and choose the less intense lines. Okay, so according to this, here's the first one, and the second one will be just here. So it's this one, this one. So for me, this is P1, and here this is R0. I'm using red for DCl37. Let's just copy the numbers. It's equal to 2098.5888 plus 2077 .3076, all of it divided by 2. This will give us 2087.95 centimeter. Now let's move to part B. In part B, he says, establish the value of Jm for each line. So let me just remove this word. Let's find Jm for each line. Already I have discussed this. So you can separate the blue lines together and the red lines together, but I'm just keeping them here as they are. Let me just erase. Okay. Let me just use the blue for DCl35. This is R0, so this has a J equals 0. So this is the value of J. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, etc. From the other side, I'm still with the blue color, DCl37. So we were here, we said that this is P1. So here J is equal to 1. So J is 1. And then we've got 2, 3, 4, 5, 6, 7, etc. أكيد بنكفيهم للآخر. Now he wants M for every level. So we know that in the case of an R branch, or for the case where delta J, I'll write here aside. If delta J is equal to plus 1, in this case M equals J plus 1. This is the case of an R branch. And in the case of a P branch, delta J equals minus 1 and M is equal to minus J. So in this case here, in the first branch, in the R branch, اللي هون بهيدي الحالة يعني إذا أنا بدي أكتب الأم هون بتساوي بهيدي هون إحنا بالR branch, so الأم here is equal to 1, M here equals 2, then M equals 3, then M equals 4, then 5, sorry, it's 4 here. 4 is here, and 5, and 6, and 7. This is the value of M. Okay, so M equals. This is the value of J for each level. Now from the other side, in the P branch, this one, we have to use M equals minus J. So here, M equals minus 1, M equals minus 2, M equals minus 3, M equals minus 4, etc. So مثل ما أنا شرحت in the lecture, الM goes 1, 2, 3, 4 for the R branch and goes minus 1, minus 2, minus 3, minus 4 for the P branch. Now this is for DCl35. What for DCl37? The same. I'm going to use the red color. So we said that this is R0. This is the first line in the rich branch. So this is R0. It has a J0. This has J1. This has J2. This has J3. And here M equals 1, M equals 2, M equals 3. Remember that M is equal to J plus 1 in the case of rich branch. And the case of the poor branch, here M is equal to minus J. So here is the poor branch. It starts from here. So this is P1 and it has J equals 1. So M is equal to minus 1. This is J equals 2, M equals minus 2, J equals 3, and M equals minus 3, etc. So you can make a table on your own, but I'm just keeping them like that. Let's move to the second part. In this part, he says, calculate for each of the two isotopic molecules the coefficients of the following polynomial E equals B plus AM plus Cm squared plus Dm cubed, where E is the energy of the line and M is an integer. I know that we know the expression. We can derive this expression. We already have derived it in the course. I'm not going to do it again. But we are able to find the coefficients doing a plot. This plot can be done using graphical or statistical software, and it will give you the coefficients A, B, C, D that correspond the best to your points. Let's write for part C. The use of a graphical or statistical software احنا اكيد مش مطلوب منا نعملهم، بس تقدروا حتى اونلاين بينعملوا على اي بروجرام بينعملوا. Establishes the following relationships. So مثل ما حكينا طلبنا من statistical software انه يلاقي لنا الكوفيشنتس للبوينتس اللي احنا اعطيناه اياهم، مره للدي سي ال 35 ومره للدي سي ال 37 هيك اعطانا. So the energy for DCl 35 equals minus 0.0006 m cube minus 0.1121 m square plus 10.6719 m plus 2091.0506. So also for DCl 37 it was found to be minus 0.0006 m cube minus 0.1117 m square plus 10.6409 m plus 2088.0547. So assume these two expressions are given. We can compare them to the expression that we have already derived. We know that E, or the energy in centimeter minus 1, is equal to B plus AM plus CM squared plus DM cubed, where B, so B is equal to nu bar minus 2xe nu bar. A is equal to B double prime plus B prime. C is equal to B double prime minus B prime. And D is equal to minus 4d bar. If we compare these constants with those of DCl35, so let's start with DCl35. So for DCl35, you can see that nu bar minus 2xe nu bar is equal to this term here. It is 2091.0506. By comparison, just compare them. And A is the one multiplied with M, so this is A. So A, which is B double prime plus B prime, is equal to 10.6719. And C, which is B double prime minus B prime, it's equal to the one multiplied with M squared, it's minus 0.1121. So as you can see, we have a system of two unknowns, B prime and B double prime. Solving this system using your calculators, just use the calculators, you will get B prime equals to 5.392 centimeter minus 1 and B double prime equals 5.2799 centimeter minus 1. Now there's left D. Simply compare the last term. So as you can see, minus 4D is equal to minus 0.0006, implies D is equal to 1.5 times 10 to the power minus 4 centimeter minus 1. So we'll do the same for DCl37. For DCl37 similarly نفس الشيء هنعمل comparison يعني. So nu bar minus 2xe nu bar is equal to 2088.0547. Now we have B prime plus, or B double prime plus B prime, it's equal to A, it's equal to 10.6404, and we have C, which is B double prime minus B prime, it's equal to minus 0.1117. So this is a system of two unknowns. Solve it using your calculator. You will get B prime equals 5.3763 centimeter minus 1. This is also centimeter minus 1. And B double prime is equal to 5.2646 centimeter minus 1. Now D is left. D is similar to up. So minus 4D is equal to minus 0.0006. We get D equals to 1.5 times 10 to the power minus 4 centimeter minus 1. هيك بنكون جبنا كل شيء مطلوب مننا. This is 9. Anyway, هيدول اتنين values. This value هو central line بحالة DCl37 و the value up هو central line بحالة DCl35. هلا هيدول must be close to the values that we have already found up. They are not the same because the upper values were approximations, but these are more exact. Here 2088, 2091. So remember that. Let's go up to see our values. So it's 2087.9, so approximately close to 2088. And this is 2090.9, which is close to 2091. Okay, so we are close. So I guess we have done part 4. part 4 said that we have to deduce the energy of the missing line, the difference nu bar minus 2x e nu bar. So this is in reality nu bar minus 2x e nu bar is the energy of the missing line. The constants b prime and b double prime, we've done that. The centrifugal distortion constant d, we have done that. This exercise says, for the DCl molecule, the literature gives the following numerical information in centimeter minus 1. The rotational constant Be at equilibrium is equal to 5.448794 and alpha E, the correction term, is equal to 0.113291. Using the relationship between the rotational constant and the vibrational level, compare the values obtained for the values of B at mu equals 0 and B at mu equals 1 of the previous problem. So we all know that B, or the rotational constant, depends on the level nu. It changes. Constant at the vibrational level nu is given by, so B for a certain level nu, it's equal to Be, which is at equilibrium, minus alpha E nu plus half. So this is the formula that we have seen in the course. Now if nu is equal to 0, we get B for nu equals 0 is equal to Be minus alpha E times half. Just substitute numbers. So 5.448794 minus 0.113291 times half. Calculate, you will get 5.3921485 centimeter minus 1. So is this value close to the one already found by us in the previous exercise? Let's see. So we're looking for B for level nu equals 0 for DCl molecule. For sure DCl 35. You must include here is 35. Okay. So let's go up to take a look. Where is it? Here it is. So this is for the level nu equals 0. It's 5.392. So is it close? Yes. So let's go back. So from previous problem, we have B bar nu equals 0. It's equal to 5.392 centimeter minus 1. So they are very close. Now for nu equals 1, B bar nu equals 1 is equal to B at equilibrium minus alpha E multiplied by 3 over 2. So this is a minus sign. So I've just substituted for nu 1. Calculate, it will give you 5.2788575 centimeter minus 1. Is it close to the value already found in the previous problem? Let's see where it is. We're talking about DCl 35. Here it is. So it's 5.2799. Let's check our value. So from previous problem, we've got B bar for nu equals 1 was found to be 5.2799 centimeter minus 1. They are very close. For the molecule CS, the following values are observed in centimeter minus 1. mu bar, which is the vibrational wave number, is equal to 1285.08, and B at equilibrium is 0.82. Calculate the centrifugal distortion constant. So D is equal to 4B bar cube over mu bar squared. It's equal to 0.82 cube over 1285.08 squared. Calculating, you will get 1.33 times 10 to the power minus 6 centimeter minus 1. Very easy.